This video is about homomorphisms, which are the maps between two groups. So let G and G prime be two groups, and the definition of a homomorphism is a map or a function, those both mean the same thing, from one group to the other, is a homomorphism if for all A and B in the group G, f of A times B equals f of A times f of B. Now, as a reminder, if the group operation on G and G prime are written with a plus symbol instead of this asterisk or just the product, then a homomorphism condition that's boxed here translates to f of A plus B is equal to f of A plus f of B. So let's look at some examples. So I'm defining a function from the integers to the integers, and it sends x to 3x. So we can write that as f of x equals 3x. And remember that the integers are a group under addition. Is f a homomorphism is the question. And so we have to check this condition or this condition. Now I wrote down or used this condition here because the group operation is addition, and so that's what the asterisk is in this particular example of the group of integers. So we have to check, is f of A plus B equal to f of A plus f of B? Well, f of A plus B is 3 times A plus B, since the function f takes x as input and multiplies it by 3 and gives that as the output. On the right-hand side over here, f of A is 3a, f of B is 3b, and so the question becomes, is 3 times a plus b equal to 3a plus 3b? And that is indeed the case because of the distributive law for integers, and so we conclude that f is indeed a homomorphism. Now let's look at a non-example of a homomorphism. So define the function g from the integers to the integers that sends x to x plus 1. And the question is this a homomorphism? Again, the group structure on both copies of the integers is addition. And so we have to check, is g of a plus b equal to g of a plus g of b? Well, g of a plus b is a plus b plus 1, since this function g takes x as input and just adds 1 to whatever you gave it as input. So if you give a plus b as input, it adds 1. Similarly, g of a is a plus 1, g of b is b plus 1, and a plus b plus 1 is not equal, in general, to a plus b plus 2. It's equal for a and b equal to 0, but the condition in being a homomorphism is for all a and b in the domain, in this case C. Okay, now let's move on to another example of this time this is a homomorphism. This is a very simple function that its domain is the integers, and the target is the integers mod 5, and it simply takes an integer and gives you back its value mod 5. So 1 gets sent to 1, 5 though gets sent to 0, because 5 mod 5 is 0. 6 would get sent to 1, and so on. Now this is a homomorphism because x plus y mod 5 is equal to x mod 5 plus y mod 5. That's just a property of modular arithmetic. Okay, and then what we see here, I've illustrated this, here's the set of integers, and here's z mod 5, it's the numbers 0, 1, 2, 3, and 4, and then we have a whole slew of numbers that are mapping to 0, then a whole slew of numbers that map to 1, and so forth. All the numbers that map to 1 are 1 more than a multiple of 5, so like 6 maps to 1, 11 maps to 1. Some numbers that map to 0 are all the multiples of 5. And what we'll see on the next page is something called the kernel of a homomorphism. It's the set of elements in the domain that map to the identity element in the target. In other words, it's the inverse image of the identity element. In this case, the identity element of the target is 0, and the elements of the kernel are all the multiples of 5. Now we can introduce an important definition. associated to a homomorphism, and that's the kernel. So let f from G1 to G2 be a homomorphism. Then the kernel of f is the set of elements in G1 that map to the identity element in G2. So in notation, it's those elements G on the domain side, such that f of G is equal to the identity element of the target side. And we have the following proposition. Let f be a homomorphism. Then f is injective if and only if the kernel of f consists of exactly the identity element. We needed this proposition in the proof of the theorem that z mod mn is isomorphic z mod m times z mod n. Well, first notice that this is an if and only if statement, so let's split up the proof into two directions. The first is we assume f is injective, and then we want to show that the kernel of f is just the identity element. Okay, so let G be an element of the kernel of f. By definition, that means f of G is the identity element. Now, we also know that f sends the identity element of G1 to the identity element of G2. And so now we have both G and the identity element of G1. They both get sent by f to the identity element of G2. So f of G is equal to f of E of G1. And since f is injective, that means that if two things are sent to the same element by f, the two elements themselves are equal. So G has to equal the identity element of G1. And that shows that the kernel of f is just the identity element of G1, since we started with an arbitrary element of G of the kernel of f. Next, let's prove the other direction. So now we assume that the kernel of f consists just of the identity element of G1, and we want to show that f is injective. So assume f of G is equal to f of h for some elements G and h in G1. What we're trying to show is that G and h, even though they're pictured as if they were distinct or different, they're actually the same. That's what it means to show that f is injective. Okay, so what I did was take this equation and multiply on the left by f of h inverse. Now, the theorem we just saw says that f of h inverse is the same as f of h quantity inverse. Okay, so since f is a homomorphism, the left-hand side turns into f of gh inverse, and the right-hand side, these two cancel each other out, if you will, and we're left with the identity element of G2. And so f of gh inverse is the identity element, that's this one out, this element here, and so that means that gh inverse is in the kernel of f. Remember, the kernel are those elements that are sent or mapped by f to the identity element. And so this means that since we're assuming that the kernel of f consists just of the identity element of G1, that means that G H inverse is equal to the identity element of G1. And from that we get that G is equal to H. And so f is injective. These two elements G and H are actually equal to each other.